Welcome, everyone. Thank you so much for joining the guest seminar series that we are putting on here at Mesmer Research Group as part of the Industrial Systems and Systems Engineering Management Department here at UAH. We're very excited to have Dr. Wirthlin with us today. He is the Senior Technical Leader for the Core Systems Engineering and Vehicle Hardware Modules and the Global Systems Engineering POV Owner for Ford Motor Company. Very, very excited to hear him speak. With that introduction out of the way, Dr. Wirthlin, I will pass it over to you.
Thank you, Amanda. I really appreciate the opportunity to be here, and a shout out to Garima, who coordinated this. Thank you very much. I'm looking forward to participating. Again, as we get going, I think we'll have an opportunity for some questions. But of course, I titled it with a little twist on Shakespeare. I'm sure he's rolling in his grave, but nonetheless, I think this is a hot topic and certainly gets a lot of buzz right now in the world of systems engineering. Before I begin, just let me just share with you some insights or some information, a little bit more about me. If you didn't have a chance to read the abstract, I've had almost 30 years working with systems engineering. And it spans lots of areas, whether it's in DoD. I've spent time as a professor in academia teaching the concepts behind systems engineering. I've worked for General Motors and Ford, so certainly an automotive bent as well. As Amanda mentioned, I currently have a great deal of responsibility at Ford, and have the privilege of working with a great team of individuals that are really trying to change the way Ford does business and trying to make our products better and smarter. I really believe in professional development and staying involved and engaged, and so I just list some of those things up there. And again, I'm grateful for the opportunities that a lot of these academic institutions gave me. And I am in COSE holding certified systems engineering professional. One of these days I'll get around to just getting the expert certification. I haven't yet, but that's more on me than anything else. Today, I do want to just again highlight that being at Ford, it's given us an opportunity and gives me an opportunity to have an opportunity across a worldwide portfolio of products targeting different markets. Very distinct areas of the world, and again with the idea of delivering functionality and capability to people to do work, play, recreate, etc. across the world. And again, it sort of all stems back from Henry Ford trying to make things go smarter and faster and deliver a vehicle for the masses. So I'm just going to highlight and set the stage of where we are today. Time is incredibly important. Consumers in general expect innovative products with new and exciting features, and just the basics of quality and safety are non-negotiable. And I'd say from my career as a military officer, certainly a lot of these things are present within the military community as well. And one of the challenges that we have is the DoD acquisition system is painstakingly slow and cumbersome. And that doesn't take these pressures away. And particularly in the realm of national security, some of our near peers and foes have much more nimble systems. And so one of our challenges is to, within our system, stay ahead of our competitors in a defense realm. And so, regardless of your background or career that you're in, I think these kinds of pressures and tensions we feel all the time. Certainly, we've heard NASA had an experience with faster, better, cheaper, and the heuristic that emerged from that was pick two at the expense of a third, and oftentimes it was not necessarily better. So we also live in an environment where more and more process is actually being levied, but they try to simplify it with all of the, whether it's lean or continuous improvement buzz that's out there. So it's, again, striking a balance. So there's even tension within our development systems on how to do things. To include, we want easier tools, yet they've got to be robust enough to handle really complex and complicated projects. And it just means that the engineer has more to learn, is considered to be competent, has to have a greater depth of capability, as well as an unprecedented breadth of understanding across different things. And so, again, even that tension within our engineering community, I think, has only gotten worse as time goes on. And then, of course, information is exploding, not only exploding in its development, but in how it's connected together. So we've got the emergence of cloud-based computing, persistence, and 2.5 quintillion bytes of data created every day. And so we become, I think we run the risk of being overwhelmed by the vast amount of information that potentially we have at our fingertips. And for the explicit purpose of doing our jobs, of trying to engineer something that will meet its stated purpose. So across this backdrop, and I'm hoping you're at least giving me the ability to say, yeah, okay, I can buy this. So across that backdrop, let's take a look back just a little bit and see how others have dealt with these same kinds of issues, but maybe almost 100 years ago. So I really like this quote that actually came out of the automotive industry, and I like it because it really illustrates the issues that we're facing today. I mean, I could have hidden who had said it and when it was said, and we'd say, oh, that sounds like today. So let me just kind of cut to the chase. In the 1930s, an engineer reflecting on what was happening then said, the engineers made all the parts function excellently, but when put together, the whole was seldom satisfactory. So from here onwards, there was a continual struggle to improve the vehicle as a whole. And I just think that is so indicative of every place I have ever worked, is that nothing ever works when we put it together, or it's difficult to integrate things and put them together. And only through really deliberate planning and rigor behind many processes are we able to get them to the point where we can put them together. And so I did a little more research. I actually read this book about 25 years ago. 20 years ago. I really liked it. Number one is it tells the stories of some pretty interesting engineering products. In this book, it talks about early defense systems, some intercontinental ballistic missiles. It talks about ARPANET, which is a precursor, of course, to the internet, as well as a massive civil engineering structure that was completed about a decade ago, called the Central Artery Tunnel, or more heuristically named the Big Dig, from Boston, Massachusetts. And this historian wrote about what made these projects unique and what did they contribute. And so as we talk about it, the 1950s, I think, is where we really began this foundation for modern systems engineering. So the first project was called SAGE, stood for Semi-Automatic Ground Environment. And it was deployed in 1958, but was considered a failure, partly because it took almost a decade to produce, and its purpose was to defend the United States against transcontinental bombers, heavy aircraft bombers. And this was a command and control system. But the process of stringing together all of the different elements, and again, 1950s, radar was a technology invented in World War II. It hadn't been around long. Radios, computers were just starting to being used wide scale, but it had a lot of notable and actually unintended consequences around how we build and put together large complex systems, and in particular, managing these systems through techniques that today we recognize as systems engineering. Now, at the same time, there's the Atlas project, which is the first of three coupled intercontinental ballistic missile projects of the 1950s and 1960s. And what was really interesting is Bernard Schriever, a brigadier general in the Army, was asked to lead, and later he transferred to the Air Force. He asked to lead the development of the intercontinental ballistic missile. And people like Simon Ramo, whose last name Ramo is the R in TRW, that some of you may have heard of, even though it's been absorbed and bought out by a lot of the others. But he is of the opinion, back at the time the book was written, that the ICBM project was the largest project the United States had ever had. The Apollo Moon project might have been bigger if it had not been able to use that industrial base that's laid down by the ICBM project. And in this book, in these first couple of chapters, he talks about how these two different programs put together constituted the emergence of systems engineering in general, partly because these projects were so massive. There were so many things that had to be developed in parallel, in virtually real time, and then they had to be assembled and put together. It led to the creation of formalized processes, configuration management, change control management, requirements management, verification, validation, and testing procedures. All of these, what we might call very simple, depending on your point of view, simple or straightforward processes can trace their origins to these two projects in the 1950s. And then later, were really put to the test in projects like the ARPANET or the Central Artery Tunnel in Boston, as again, all these moving parts were coming together. So yeah, and on top of that, they were socio-economical issues as well. There were political issues, there were communities of people, whole coalitions coming together that had to figure out how to make these things work. And I think this is a really important underscore to everything about today's practice of systems engineering. We have to be able to work together, and we have to figure out how we can do things in this environment, talking about all those tensions and pressures that we have and that exist in the systems today. So just going forward, again, for some, it's this is basic foundation, but it's a way about thinking and seeing the system as a whole. You know, the idea of being greater than the sum of its parts, and that we can't optimize parts. Rather, we might want to focus on optimizing the system. So this picture over here is a great example of systems thinking and some good systems engineering that happened today. And in this case, it's the power on board, the Pro Power on board that Ford has built into some of its F-150 trucks. It has customer-friendly tailgate and work surfaces. There are even depressions in the molded plastic on the tailgate where you can put pencils, where you can attach clips or other things to hold, clamps to hold power tools in place. And then again, just recently this past winter, we saw that when the power outages went across Texas during the freezing weather that they encountered, customers turned to this particular feature to use it in ways that were unintended and unanticipated. And that was to power their homes and to keep themselves warm. These generators that were built in as part of this product, never intended to power a home, actually turned out to be used that way. And so all of these things come together. Now, again, I think we talk about why systems engineering. Don't want to belabor it, but I think this is in just about every engineering textbook today. This idea that systems engineering has the greatest design influence up front and early before we even start contemplating parts, as we go through the different aspects of a product development process, because we can focus on what is the end state that we're looking at, and we can make those optimization trades at the product level or at the vehicle level, or the systems level, as opposed to the tension that exists within a company to only optimize around a part. The other thing that I think that is really interesting as systems engineers in general, and I'm happy to be talking to the department, is that we play a variety of roles. And I think it's interesting from a school perspective. You know, many times some of these roles end up being filled by professors and teachers' assistants while we're in school. In the real world, though, there's no one to really ask, did I get the right answer? We have to figure it out. So in some sense, our professor and TAs, they give you the requirement, they tell us the schedule, it's got to be done before the test or before the end of the semester. They dictate what processes we're going to use, and ultimately grade us based on the testing that we've done or the way that we've delivered it. And we said, yep, we were able to get the answer or not. But in the real world, we don't necessarily have that, except to say, did we meet the requirements that our end user levied on us, or what the market is demanding? In order to get there, though, you can see that all of these different roles, I think, shoot, I forget the name of Sarah, prolific writer. She's the one that came up with these different roles within systems engineering. There's a great paper on it. Sarah Sheard, there it is. It's right there in my footnote there. Sarah Sheard was the one that kind of said, hey, we fill lots of roles. And some of these roles are really informal, and some of them are really pronounced. But through those roles, we're able to deliver some benefit and rigor. And I think there are probably 3 or 4 major benefits. Yes, this book exists, by the way. If you don't have it, it's kind of a fun one to have. But system engineering is not for dummies, that's for certain. When we implement system engineering, again, we can see the traceability of our data throughout the life cycle. We can get to things when and where we need them, and we've got collaboration. And that's why, again, it's Sarah Sheard had talked about this role of having a glue engineer. Now, again, these are all great benefits that when systems engineering is done well, it can happen. And given my experience in the DoD, I would say that largely, particularly on the largest of development programs, systems engineering plays a key role. It's very labor intensive and has been for decades. And I'm going to just show you an example that because of that, the intensity of the labor, because of all of the different roles that system engineers play, and unfortunately the silos that sometimes have unavoidably crept in between all of the different disciplines that work together, systems engineering oftentimes has looked like this. So this is the process as drawn on the back of the napkin, or I'm being a little facetious. This was a cartoon that was presented in the 1970s, and it just shows that the customer wanted a tire swing, but the RFP or the requirements stated one thing. The person who was doing the work understood it. What was actually specified by the designer was something else. What was designed by that designer looked a little different, and then the way it was actually implemented looked something like this. And we laugh and we chuckle, and I think all of us can resonate with that, regardless of how much experience we've had, just because we've seen it happen. Large school projects, we misinterpret things, we understand things differently, and sometimes we go down the wrong direction, when in reality it could have been so simple. So this is sort of what many people thought of systems engineering in the 1970s. Well, this same source back in 2012 said, okay, well, let's fast forward. And now, as you look at this, what's different? Well, it's in color, and I got more steps. All right, I had more things that I had to do. You know, I don't know about you, but the definition of insanity is trying to do the same thing over and over and expecting a different result. But this is where many people saw systems engineering and continue to see system engineering today. And oftentimes the answer, and I truly believe with the Department of Defense, the proliferation of reviews and processes and different things that have to happen come because of quality spills or mistakes or things that happen, which end up adding more and more steps to our process. So aside from that, this is what ends up happening. And I'll be fair to say, even within Ford, if you look at our Ford internal product development process, it also has a lot of evidence of additional things that continue to get brought in and added to the product development process. Most of them, in terms of a lean vocabulary, would be what I would call quality checks, where we check and make sure the quality is there rather than designing it in or building it in from the beginning. So again, this is sort of the paradigm that many people have today, and I think many people at Ford still believe that this is what system engineering brings. It brings a lot of paper, brings a lot of process, and it's not value added to me. But we're going to show them, we're going to prove them wrong a little bit, or at least I believe we can. So again, here's heuristically what we say system engineering can do. It has a different risk profile, but it also, if we spend more time up front and really figure out what it is we want to do, we are able to shorten significant portions of the rest of the product development cycle, such that we actually deliver earlier, much earlier, in fact, than we would have through a traditional system. So how do we do that? Well, let's go back to those different roles that we're talking about. So I think many of you are familiar with Eric Honor, who wrote a PhD on the return on investment for systems engineering. And he broke down activity, system engineering activity, by different capabilities, whether they were understanding the mission or the use cases, requirements, the architecting behind it, the integration, testing and evaluation, and those that were successful on the left-hand side of this graphic spent much more time really trying to understand, what are we trying to accomplish? What is it that we're trying to do? And because of that, the time and effort spent in integration and test and validation at the end were significantly decreased when compared to those that didn't do so well. And then on the right-hand side, you'll see this capabilities in certain areas of systems engineering really do correlate strongly with performance and success. And this was from a study done by NDIA back in 2007. And again, it puts architecture, trade studies, understanding those early principles upfront and early is to be really important. So let me just move forward. And again, that's showing that, oh, you know, this might be the overall answer, but going back, that when you're organized correctly and you have a right mix of things, you actually do better. Okay, so let's look about engineers. Now that if we've established and accept the premise that maybe systems engineering can help, now we have to implement it. Well, how are we actually spending our time? So this is some, at least one study that's out there. There are many more, and I left them out for the sake of time. But 50 to 80% of an engineer's time is considered non-value add. You know, one database claim I did find from 2015 was that engineers actually spend 75% of their time not doing real engineering. And here's where a lot of that time was spent. It was either understanding, doing tools or process, or chasing or following up data, which again, if at least for me, this rings true. It passes my personal giggle test, because this is how I found my work day going, where I needed to find the information, and sometimes that took up most of my day. I also came across this study back in 2000, and I like it because, and I had an aha moment as I was reading it, that engineers or people involved in product development, here it's called design engineers, but there's a pattern that was observed and documented, and it was really fascinating, that engineers will go to the requirements document, but not to necessarily find the requirements, to find out who wrote it. Then they go to that person oftentimes and will seek to get more information or more documents from that person, and then begin to interact socially. And as they come across other documents or other things that inform them and help them shape that opinion, they go and actually try to find that person or persons that is an expert in that area. And so there's an interplay that goes on between documented sources and engineers that help a designer, whether they're a system engineer or a designer in general, to do their job. Now, think about those requirement documents. That documentation really talks about, this is how we do the technical solution. But the context of how they arrived at that written information is nowhere to be found. And in this paper, they lamented that fact, and they suggested that different levels of abstraction, that there be ways to document them that could include the context, that can allow us to, again, engineers' choice of written versus oral information sources is that the concrete product information is in documents, but the context comes from people. And so, as from another study here, back in 1993, the reason why engineers spend so much time looking for information is that it's difficult, no question there, but there's a lot of silos and stovepipes out there. Finding what you need, distributing that information is difficult, but it's really high. And the DoD just has a lot of money that they can throw at this problem, honestly, where they can get around some of that. And then there's a lot of interdependency. If I make a design decision in one area, there are propagating second, third, and fourth order effects, even more, that can go throughout an entire system that, if taken and done in isolation, we lose completely. And then finally, finding or developing a system to design a system is very difficult and remains beyond the grasp. And this particular paper was published in 1993, and one of the things that made me chuckle is in a side note to this particular comment, mentioned that, but we have fax machines and cell phones now, and so that's going to really help us. So again, I love this quote: solutions will arise when we realize that they have to be system solutions, where the system is redesigned as an integration of people, process, and technology. And I realize I'm talking to the choir here. So again, one more thing. This is a picture of an engineer. He and most other engineers I know don't love writing or managing requirements. They don't enjoy updating FMEAs and P diagrams, particularly if I'm just changing them to put them into different formats, because that's how they're consumed by another process downstream. I don't like having to go through to mine or manipulate data to update things. Maintaining traceability is really hard and something they don't like to do, and I also don't like to reformat them. Is there a way that we can maybe take an approach, perhaps a modeled approach to address these and other non-love seemingly value-added activity. So that leads me, and here we are almost 30 minutes later, to the question, model-based system engineering or not? Is that really the question? I ask that because when you look at what MBSE purports to do, okay, and I have them listed here, decompose, there's an architecture or a hierarchy or an abstraction to that. There's relationships. We talk about requirements, that it enables functional modeling, it enables physical modeling, and we desire through using model-based system engineering to facilitate interoperability of models, even if the tools and simulations used are really heterogeneous. They're different, as well as describing how we verify and validate and how we strike the balance between design and production. So as I was putting this slide together a few weeks ago, I came across a comment that a PLM vendor, and they'll remain nameless, and the tool that they represent, but they said there are 3 foundational concepts that we just can't get rid of in PLM or the product line management or the actual building of systems of things, cars, vehicles, etc. You have to have requirements that are parameterized, that they're very specific. You have to have architectures that you can tie them back to, and you need to have simulations present across all of those different types of requirements, all the different types of architectures, etc. And so I'll just give you a window into what Ford is doing in that thing is we have 4 levels in our architectures that help us understand and ask the right questions to ask and when we answer them. So first we conceptually say what problem's being solved and contains use cases and other things. At a logical layer, we try to say, how could we solve this problem agnostic of actual technical choices? So how would we break down our use cases into smaller logical components or rational groupings of requirements that could be taken care of, and then we would proceed to a technological layer where we look at specific ways, hardware and software architectures, mechanical architectures, specific technologies. Do I want to use, and again, I'm thinking from the context of a vehicle, do I want to use a LiDAR? Do I want to use a radar? Do I want to use a wheel speed sensor? Do I want to use a calculated sensor? Do I want to use a GPS speed in the applications that I have? So now I'm starting to make very specific technology choices. And then at the implementation level is, okay, we've decided what we're going to build. And again, this is an architectural construct which is very standardized, or rather could be standardized. It adheres to or is closely aligned with the ISO standard around architecting. And we intend to use it. Now, I'm just going to tell you why we use it is as we architect our systems in automotive, our profit is driven by volume, not necessarily by margin. So we often end up having discussions around pennies or parts of a penny of profit that we might gain on a particular item, that when we scale it to 1 million vehicles, that's a lot of money, right? So we end up having to reuse a lot of things, and we want to drive the reuse, which we see already in the product themselves. Many parts are common between many different vehicles, but even in our engineering space, if we don't have to recreate a similar simulation, for instance, every time, if we don't have to recreate requirements at a high level, for instance, well, we can. So if we don't have to recreate these things or these things, we can spend our time applying them to technology as it changes. We can spend our time building variants of different vehicles and focusing on the unique things, the differentiators between our products that we sell to the consumer, as well as how they differentiate us from our competitors. And so, that's an approach that we use to help us articulate things. The other thing is we do believe that we are in the midst of a paradigm shift. A couple generations, we went from drafting and documents to CAD to CAE, and nobody is going to go back to that way of doing things. So, check that box, but now we never quite moved out of our requirement document. So here's another interesting thing, and this is just trivia from my past. The B-52, the original requirement specification for the B-52, again, a bomber that was designed and conceived in the early 1950s. That original specification was about 3/4 of an inch thick for what was wanted for the B-52. Today, many of our systems, particularly in the Department of Defense, it takes truckloads, literally truckloads of data to deliver all of these requirements. Well, how is any competent engineer truly going to be able to consume those documents and understand them and grasp them? We can make them machine readable, but again, can that engineer truly understand them and consume them? But if we go to a model, well, with the model and the descriptive capabilities and making them semantically rich, that can now drive and inform many of our math-based simulation and analytical models that we have been doing for at least 2 or 3 decades. And this now provides the opportunity to, because they are there, to have the data linked, to be able to visualize what it is we're trying to deliver, and can provide that traceability that's there. It's really easy, and it's a temptation, I think. And anyone who's been a student knows exactly what this is like. They're given a project and they immediately go and they start designing things. So we see this in this diagram today. We get some initial requirements. We might try to break it down in some high-level things, and then we say, okay, I'm going to go straight to the solution. And oftentimes we lose exploring quite a bit of that design space. But if we can break it down into that reusable space, where we look at things from a logical layer and understand what is the functionality that we're trying to deliver, we can reuse this piece over and over and over again. That doesn't change with technology. Of course, as new things get invented, as new concepts or new use cases arrive, we would go through and build out these first 2 layers, but we can do a lot by reusing this layer, and then we can spend time on what's the right technology, how do we pick the right variants, and then when we're done, we have that bill of materials, that bill of features, that bill of software, that bill of materials that we can then use to build our product. So let me just kind of recap a little bit. Engineers have a hard time capturing that design rationale. There's lack of integration. How do we distribute it? And there's a lot of design interdependence that we have to be able to pull together. How do we do it? Well, it's basically forcing that convergence between MBSE and MBE, and there's no magic button. But the payoff is real, and the payoff comes in higher quality, and we can do things potentially at a faster speed. And this is an example. So for instance, across the systems engineering V, and I'm not going to debate whether the V is the right framework to use, but it's well known, well understood. Across the V, We can focus on early types of models that provide the context and that can provide that traceability. And then we can connect them and use them together with existing models across CAE and as well as into actual hardware validation. And we can go back and then validate or determine where our models still need additional work compared to the actual delivered product. So again, there's where a lot of our model-based system engineering tools can go. Here's our CAE models, and then we actually verify with the finished product. So again, I think engineering needs to be model-based. It's got to be across the spectrum, and it's got to go from the very early stages all the way to the end. Simply stated, and this is straight out of the podcast about system engineering, projects that do more system engineering perform better. They meet their budgets, they meet their schedules, they meet their technical performance. It's clear across the board. Projects that do more are better in all three of those categories. The money that is spent on system engineering has a very good return on investment. And so when we ask the question of MBSE or not MBSE, I really don't think we can, that's the question, given the velocity of information, our reliance on software, the complexity of our social technological systems today, and the pressures that we're under. It just drives that we have to, it's an essential and mandatory component to developing and producing systems and products in the product development chain. So I went through this really quickly. I want to thank you for the time, and I'm happy to take some questions. Before I do take some questions, again, one of the things that I had a lot of fun with putting this together, that first system that I talked about, that SAGE system, which was an early warning radar system for the military, even though it was considered a failure because the threat changed, the use case changed, that it continued to play a role. And my last assignment while serving active duty as an officer is I was in charge of the battle control management programs for the Department of Defense from the acquisition perspective. And it was a system that was multinational. So we had Canadian partners. We had, it was redundant, meaning that we had 5 different centers of operation, that if something bad were to happen to one or any of those other 5 systems, another location could pick up the functionality of that system that was somehow knocked offline or unable to perform the function, and could still carry out the mission. And so, in this case, the use case changed yet again, where it wasn't so much the threat of ballistic missiles, but now it was the threat that was the use case of using airliners as a terrorist weapon that came out of 9/11. And so it sort of came full circle for me that I, learned a little bit about SAGE and systems engineering in school, but then at the culmination of my military career, I was thrust back into a very similar role, trying to design a robust system that could protect the continental U.S. And so for me, this was really a lot of fun to put this together. I thank you for your time and your interest. And I hope I answered some of your questions, or at least provided you some provocative things to think about. I'm happy to take questions.
Well, thank you so much. This presentation has been really phenomenal. We've had a couple of people ask in the chat, are your slides going to be available after the presentation? I know we'll have the recording up. Okay, wonderful, wonderful. I know a lot of people will be excited about that. Thank you.
Sure, happy to do that. Other questions?
So I'll start things off if the students aren't going to chime in just yet. So you showed a pyramid of architectural levels.
Sure.
How did you come up with that? Is that just through experience and through Ford processes that you kind of develop that, or is that something that you based off of something else, or how did that come about?
Well, I think it was a journey of discovery, and let me just say right up front that it was not my creation. I mentioned the great team that I work with at Ford, and one of my team members has a great background in computer science. At one point, worked for Google. Has a lot of software background, and a lot of that architectural pyramid was borrowed from the ISO series around. It's actually called Software and Systems Engineering Architecture. So we borrowed a lot of material from that. This gentleman is Dr. Asan Komar, and he borrowed a lot from just his experience working in different environments, and also referencing that ISO material. And in some ways, Ford was already doing some of that. We had organizationally divided ourselves into some early conceptual work, as well as the actual design and downstream implementation. And so, again, being pragmatic, because time is money and we're trying to get product out the door, we tried to find an abstraction approach that would complement our existing organization, which is still evolving and will continue to evolve. But we also wanted it to remain based in international standards, so that as different vendors come online, as different techniques emerge, if you're built on a foundation of international standards, the likelihood of huge sort of tear up and throw away of a corporate process is reduced significantly. So we're trying to think long term. Again, we're trying to take a systems engineering approach of how do we practice what we preach and yet remain effective.
Great, thank you.
We've got another question in the chat. What is the difference between system certification and IV&V exercise?
So systems. So I would say that this is stretches the limits of what I'm an expert in. But certification is typically bound against external rules, external reference points to say, yep, okay, I've met certain standards, I've met certain things. The verification and validation, I think, is really a tool that an engineering activity really needs to take advantage of. And fundamentally, it's just, do I know that I built the right thing, and have I built the thing right? That's the idea behind verification and validation. Because, and again, many cases in my own career, but I think it will resonate with a lot of you. You can follow every single thing perfectly, and it's the wrong answer, or it doesn't really do what you thought it would do. So it failed. A really important component is, did I build the right thing? And so those two go hand in glove. But if it's done well, it's really for the organization that's doing it to make sure that they've kept their focus where it needs to be, and that they've done it correctly. Now, off the cuff, so I'm sure there's somebody out there that's an expert in it and can correct me.
Well, we have a little bit of a follow-on to that. Do you consider prognostics and health management, a PHM, as part of the systems engineering domain?
I would say we ought to be consumers of it, and we ought to bake it into the design and requirements that we would expect. I wouldn't purport that we would run it, or that we figure out how to do it best, but I believe that that's essential to address the tensions in the system that exists today. market pressures and others that we talked about.
Thank you. It looks like we've got a
Question.
couple more questions. Go, Garima.
Oh, okay. Hi, Robert. Thanks for doing this. Love the presentation. So on one of the slides, you mentioned the advantages of MBSE. You said, improving quality and then potentially saving engineering time. I know we've been doing MBSE for a while now, especially in the features area. Have there been any internal studies conducted to devise these metrics or to assess the value of MBSE?
There have been, and I failed to stick it in here, so I apologize. But there have been some studies where, if I had it, I'll find a slide and I'll throw it into the deck that will get distributed later. But it's a study. Again, this was based on against a Department of Defense contractor, and they were 3 different programs that the DoD contractor was working on, and the first 2 programs did not use model-based system engineering, and the third one did. And what was interesting was it wasn't so much the time that was affected by model-based system engineering, at least by this particular measure. So this is one sample, right? It wasn't so much the time, it was that the number of requirements that were actually created by the model-based approach was several order of magnitudes higher than the requirements in the other 2. But when they looked solely at software and or hardware errors or misses, by several orders of magnitude, the programs that did not have model-based system engineering had again, by orders of magnitude more misses, more rework that was required, et cetera, than the one that was model-based. And so I'll need to get that one. NDIA, as well as the SEI, who created the CMMI and other things, they have published, I think in 2007 through 2013, a whole series of research trying to really tie down the benefit of using model-based system engineering. So that was so the first one was by Delgatti and Associates. I think you could even Google it. If you Google Delgatti and Associates systems engineering return on investment, you'll find that one slide that I mentioned, that study that I mentioned. The other one comes from SEI and NDIA joint study that we talked about. And then there's some other items that are out there, or other studies that are out there that said, well, okay, I'll use just plain old system engineering. What if I used MBSE? What does that do for me? And then what happens if I do model-based product line engineering, which is yet another type of engineering focused on managing variance in the engineering world, as opposed to managing variance at the part level. And product line engineering is actually a brand new ISO standard that was just released this year. So there was regular system engineering, there was MBSE with system engineering, and I think it cut it by about 30%. And then product line engineering cut the time by about 60%. I'll try and throw both of those slides in that, but there were some significant savings done. If I were, the only soapbox that I would get on, and maybe something that the program here might want to look at is if you teach people product line engineering, that would be a huge differentiator between what other schools are currently teaching right now. Product line engineering is kind of an organic thing that a couple of companies, one in Europe, one in the US, came up with. I think they both have their basis in PhD theses. So one of these days, Garima, you'll come up with the Garima technique, and And that'll be another way that'll get us ahead. But anyway, we could spend a whole nother discussion about product line engineering. I'm certainly not the expert in it, but I've seen it at work. I've seen how effective it can be. Particularly at my time at GM, I saw how they use that to save significant amount of time and effort. So the evidence is out there. It's a little bit spotty. It's a little bit scattered. And of course, as system engineers who have done this and practiced this anywhere, typically we hear, oh, but wait a minute, I'm different. It may work over here, but I'm different. It'll never work in medical devices, or it'll never work in consumer devices, and so on and so forth. And just from professional colleagues and the associations that I've had, yes, Procter & Gamble is working a lot in this area, and it works. Medical devices, it works. There's a lot of medical devices that are using it today. Both MBSE as well as PLE works in the energy sector. It works in the gas and oil industry. So, of course, aerospace was sort of where this got started with Department of Defense contractors. But it works, and it's growing.
Thank you.
So that was my short answer.
Well, thank you so much. It's all been so informative. We have a couple more questions, but we are at time. So do you want to take those questions, or do you have other?
I have a little bit of time I can go over if people are okay with that.
Okay. Well, I will ask them real quick then. First question, do you foresee MBSE ever becoming obsolete or outdated?
I foresee it becoming sort of part of the way we do engineering. I expect MBSE to change. There's an effort going on right now that particularly those who define MBSE as being based on the systems modeling language. There's an effort to sort of build on that foundation, and it's going through the international standards committees to be approved as an international standard for SysML 2.0. So I think it will constantly evolve. It will constantly change. A decade from now, it will probably look a lot different from what we understand it today. But I think, again, given the tremendous pressure and the amount of information we have to consume and what we're trying to do, if anything, the acronym will go away, but it will just become part of the way that we do business. That's how I would foresee it.
Wonderful, thank you. All right, and our last question. You stated that we want more process, yet simplified. From your experience, how much explanation is needed to get people to adopt the processes?
It's not so much explanation, it's I think there's a level of skepticism, and when people see that it works, then they are willing to do it. And that they're willing to stick with it when they see somebody deviate and it results in a problem. And that's one aspect. The second aspect is I believe there's great value in continuing to try to simplify our processes and asking the question, what is the value add associated with that process? And a great example, I think, is that so much of what we do today is it's the Conway effect, right? Our organizations are designed on how we do the work, and our processes are often designed according to, unfortunately, the way a tool was architected, or the way that the tools that we have were strung together to create the product. So with the application of Conway's law and the tools, as tools improve, as computing power increases, things that would take days or weeks become minutes and days. That will change a way a process might work. It will change how it flows. It would certainly change perhaps even how we're organized. So I think that we need to remain vigilant to look for ways to improve our process, look for ways to simplify, which I think goes hand in gloves with improving the tools and the confidence that we can put into the results of our simulations and everything. I mean, if you think of the automotive industry in particular, it used to be clay, everything was done in clay, everything was done with a physical prototype. And yes, today we still use clay models for some things, and we still do physical prototyping for some things, but at a significantly reduced number, which has saved the company tremendous, and the industry tremendous amounts of money, because they can do it virtually now, for instance.
Can I ask a quick question?
Sure.
Yeah, so my question is kind of along the lines of the previous question, which is, what do you perceive it will take to mature the discipline of model-based systems engineering? What I'm thinking of is with like other engineering domains, you have your like finite element analysis and computational fluid dynamics that have strict mathematical equations that govern the way the models exist and are interpreted. And so for MBSE, you have, depending on both the language and the tool, you have different interpretations and different makeup of the models.
Sure. And that's a really good question. So some vendors have taken upon themselves to define a methodology as well as implementing the language. So in their modeling tool, and I'm thinking of companies like Obeo and others, they are very proscriptive as to how something is done. SysML, just in and of itself, it's a language, and you can manipulate that language. It's extremely flexible, right? So Ford came up, and again, it happened far before I got to Ford. They developed their own style guide and methodology, and actually Garima has been leading quite a bit and doing quite a bit of work helping us expand that style guide and methodology to other areas of the business that we've never done before. And she's probably better suited than I am to even ask that she could share her growing pains, if you will, of trying things, going in a direction it doesn't work, but eventually finding ways to express it. And I think that's a reflection on the fact that we're, as a discipline of using MBSE, there's still a lot to be sorted out. I think of the early electrical electronics or electrical equations. The concept of a resistor, the concept of a diode, the concept of a capacitor. In the early phases, there were different ways to represent them, different ways to talk about them. And now today, I mean, you look at that symbol and you know exactly what it is, right? So there's some of it is just through use, through wide distribution. And I think, again, that goes to my saying of eventually MBSE is not this appendage to model-based engineering. It's just part of the whole flow. And things flow, somewhat ubiquitously across the different tool boundaries and disciplines that use it. We're on a journey.
Thank you.
All right, that is over time a little bit. Thank you so much for staying and answering those questions. We really appreciate it. This has been a phenomenal talk. Thank you everyone for attending. We will make all of the presentation materials and the recording available within the next few weeks after we do a little bit of cleanup and get those in a format that we can share. Everyone, have a great afternoon. And Dr. Wirthlin, thank you again.
My pleasure. Glad to be here.
Thank you.